Welcome to this next class of Dielectrics, in which we are going to see some remaining part of the chapter Dielectrics. In this class, we are particularly going to see the Clasius-Mossotti equation. As you may remember that we have learned that the dipole moment, that is small p, for a linear dielectric. A linear dielectric is a dielectric in which the dipole moments align in the direction of the external electric field E. The dipole moment is directly proportional to the electric field. So we have a constant which is the alpha for the dipole moment. Same way we have the for the polarization vector, this polarization vector is for the whole substance, whereas this dipole moment is only for the molecule or the atom. This polarization vector is also proportional to the external electric field, and when we remove the proportionality sign, we get a constant which is xi into epsilon naught. This xi is the electric susceptibility. So polarization vector is also proportional to electric field, and the dipole moment is also proportional to electric field. The Clasius-Mossotti equation gives us a way to find out this alpha. So this alpha can be given by the Clasius-Mossotti equation as 3 epsilon naught divided by n into bracket epsilon r minus 1 divided by epsilon r plus 2, where n is the number of molecules in the dielectric substance, epsilon r is the relative permittivity of the medium. So we can easily find what this alpha is, which depends on which is actually the constant at the molecular level or atomic level. So let us see how this derivation is done. To derive this, we will have to consider a parallel plate capacitor. A parallel plate capacitor, one plate is having negative charges and the other plate is having positive charges. We have placed a dielectric in between these plates. Inside the dielectric, all the molecules will get aligned in the direction of the field, because we are considering a linear dielectric. The positive charges will align towards the negative plate and the negative charges will align towards the positive plate. Now, to find out the electric field at a point, let us consider O. We will have to draw a sphere around this point of radius r. Then we can show this same configuration as like this. In this configuration, these are the bound charges. The in between charges will get cancelled out and there will be charges left on the sphere. On this side positive charges, on this side negative charges will be left. These are the charges at the surface. These are positive bound charges, these are negative bound charges. These are the free charges, that are the charges which are present on the conductor. These are also the charges which are present on the conductor. So the electric field at this point O will be a sum of electric field due to this free charges, electric field due to this bound charges, as well as the electric field on the surface of this sphere and the electric field due to the molecules which are inside this sphere. So let us give them numbers. Let us say the electric field due to free charges is E naught, the electric field due to this surface bound charges is E1, electric field due to the charges on the surface of the sphere are E2, and electric field due to the molecules inside is E3. So the electric field at point O will be the net electric field due to all these fields, that is E naught plus E1 plus E3, E2 plus E3. Now electric field due to E1 can be easily determined as it is equal to sigma by epsilon naught, and we can replace this by d divided by epsilon naught, where d is the displacement vector. As we know, displacement vector is equal to free charge density. This equation we have already derived in previous classes. Also E1, which is due to the bound charges on the surface of the dielectric, is minus P divided by epsilon naught. This electric field due to bound charges will be in negative direction or opposite direction to the electric field due to this E naught. Electric field, as we know, is directed from positive to negative charge. Inside the dielectric, it will be in opposite direction, that is positive to negative. That is why we will get this as negative. Now to determine the electric field due to E2, that is the charges on the surface of the sphere, that is negative charges on this surface and positive charges on this side of the surface, we will use a trick. What is that trick? Instead of considering that configuration, what we will consider is two spheres in which there is volume distribution of charge. The charge is present inside the volume. We will consider two spheres. In one sphere, we will consider a positive charge distribution inside the volume, and in one sphere we will consider negative charge distribution inside the volume. Now if you combine these two spheres, what you will observe is you will get the same charge configuration. See, if I combine them like this, you will get the same charge configuration. On this side there will be negative charges that will be left. On this side there will be positive charges that will be left. The charges which are present in the overlapping region will get cancelled. So I have drawn this diagram which will imitate or which will be similar to the charge configuration that we have for that sphere. Positive and negative charges on the surface. So we are going to consider this negative charge volume density and positive charge volume density to have combined and created this type of charge configuration. Now O1 is the center of this positive charge sphere and O2 is the center of this negatively charged sphere. Now we are going to find the electric field by considering a point A, and we are going to determine the electric field due to this positively charged sphere and negatively charged sphere. So if we consider the positive charge, with charges distributed in the volume, then what we want is the electric field at some point A. Here we will be using the Gauss law. We will draw the Gaussian surface around this point. This is the center, let us call it O1, and this point A is present at a distance, let us say R. Now we know by Gauss law we have E dot ds is equal to integration of E dot ds is equal to Q enclosed divided by epsilon naught. Now this Q enclosed we can find by taking integration of this volume charge density, that is rho, into volume, that is dV. So we can write this equation of E ds. E will be constant, we can take it outside, into ds will be equal to rho will be constant, we can take it outside, into dV, integration of dV divided by epsilon naught. Now integration of this closed surface integral of this ds will give you 4 pi r square, whereas integration of this dV will give you 4/3 pi r cube divided by epsilon naught. So we can cancel this 4 pi, r square will get cancelled, and what we will get for positively charged sphere is rho r, this will be r1 in the direction of that field divided by 3 epsilon naught. Similarly, we can write for the negatively charged sphere as minus rho r2 divided by 3 epsilon naught. And now we want a net field because of these two spheres, because we have combined these two spheres and we want a field at this point A. So the net field due to these two will be E plus we will get E of this minus. So if we write these two factors, we will get sigma r1 vector r1 divided by 3 epsilon naught minus sigma r2 vector divided by 3 epsilon naught. So we can take this sigma and 3 epsilon naught as common, and we will get vector r1 minus vector r2. Now vector r1 minus vector r2, if you see in the diagram, is nothing but d vector. Vector r1 minus this vector r2 will give you this d vector, which is directed from the O2 to O1. So we can replace this r1 minus r2 by d vector. So this will be the net electric field. We can further simplify this equation by writing the equation for the rho. Rho is nothing but charge divided by volume. Rho is nothing but charge divided by volume into d, that is the distance between the charges, distance between the center O1 and O2. Now these centers, we can consider that for a volume charge distribution, the charge to be concentrated at this center O1, and for the negatively charged distribution, we can consider the charge to be concentrated at this center O2. So this Q into D will become charge into distance between the charges. Charge into distance between the charges, as we know, is dipole moment. Dipole moment P divided by volume, and we have 3 epsilon naught. Now dipole moment divided by volume is nothing but polarization vector, So we get an equation of E3 as polarization vector divided by 3 epsilon naught. Now finally, the electric field due to the charges inside the sphere, it will be 0, because the charges will be both type, positive and negative, and the net charge will be 0. So the electric field due to them will be also equal to 0. Now we can write what is the field at O because of all these contributions, E0 plus E1 plus E2 plus E3. All things we have found. Okay, sorry, this is E3 and I think so this was E2. So for E0 we have displacement vector divided by epsilon naught. E1 is minus polarization vector divided by epsilon naught. E2 is polarization vector divided by 3 epsilon naught, and E3 is nothing but 0. So now we can combine this. We will get polarization displacement vector minus this polarization vector divided by epsilon naught plus polarization vector divided by 3 epsilon naught. And if you remember, the displacement vector we have shown that it is equal to E0 into epsilon naught plus this polarization vector. So D displacement vector minus this polarization vector can be also written as epsilon naught into E0. E0 is the electric field due to free charges. So let us replace this quantity. So we will get E, the net electric field at point O will be E0 into epsilon naught. Epsilon naught is not a vector, divided by epsilon naught plus P divided by 3 epsilon naught. So this will be the net electric field at this point O due to different charge configuration. We can cancel this epsilon naught also, and we can write electric field in the medium. Now point O is inside the medium, so this is the electric field inside the medium will be equal to E0 plus this polarization vector divided by 3 epsilon naught. Now we are going to go back to previous equation. Let us call this equation number 1. We have dipole moment, or we have dipole moment small p equals to alpha into electric field due to the electric field inside the medium. So we can write, and also one more relation is there, polarization vector p, this is small p, polarization vector is equal to n into this dipole moment, where n is the number of molecules in a volume. So we can combine this, and what we can write is this polarization vector P, polarization vector capital P is equal to n into dipole moment. Dipole moment is alpha into Em. Now from equation 1 we can replace this Em, we can replace this Em as n alpha. Em we have derived is epsilon naught plus P by 3. Epsilon naught is E naught, that is electric field due to free charges, plus P divided by 3 epsilon naught. Now we can substitute this polarization vector also, as we know polarization vector is equal to xi epsilon naught into electric field. So this xi plus 1 is relative permittivity. So we can write this xi as relative permittivity minus 1. So polarization vector can be replaced by relative permittivity minus 1 into epsilon naught into E naught. Okay, now let us replace this polarization vector in the above equation. So on the left hand side we will get ER minus 1 into epsilon naught into E naught is equal to we have n alpha E naught, n alpha in the bracket we have E naught, that is electric field due to the free charges, plus polarization vector we will replace by relative permittivity minus 1 epsilon naught into E naught divided by epsilon naught. So now this epsilon naught we can cancel. We will try to multiply the terms which are inside the bracket. N alpha we have epsilon naught plus ER into E naught, we have E naught into minus we have this epsilon naught. Okay, see I have made here I think so 3 is also there, so we will have here divided by 3. We can multiply this 3 on this side and we will get n alpha 3 E naught plus E naught into epsilon r minus epsilon E naught divided by 3. So further we can write this as n alpha we will have 2 E naught plus E naught to ER divided by 3. Here we can take E naught common outside, 3 we can take here, and in the bracket we will have epsilon r plus 2. On this side if you remember we have epsilon r minus epsilon naught into E naught. Epsilon r minus 1 into epsilon naught into E naught. Okay, now we can cancel this E naught also, and we can get an equation for alpha. Alpha will be equal to 3 into, sorry, this is epsilon r minus 1 divided by n, and epsilon r plus 2 will go on this side. So this will give us the equation that we wanted. I think so I have forgotten here epsilon naught, so it will be 3 epsilon naught epsilon r, that is relative permittivity minus 1 divided by n into relative permittivity plus 2. Now this will easily give us what is the value of alpha, which is the constant at molecular or atomic level. Now while deriving these equations we have made certain assumptions. So this equation will be applicable only for neutral dielectrics. This will be applicable for neutral dielectrics because we have considered the polarization to be directly proportional to the electric field. That means all the molecules will align themselves in the direction of the electric field. So this equation will be mostly applicable for neutral dielectrics. As we know, there are two types of dielectrics. One dielectrics in which have permanent dipole moment, and other type of dielectrics are those dielectrics which do not have permanent dipole moment. So these are polar dielectrics where we cannot apply this equation, and this is neutral dielectrics where we can apply this equation of Clasius and Mossotti's to find the alpha. So thank you.